I think we can start. So today we are with Felipe Delgado-Aparicio. So he's original from Peru, where he's got his degree in physics, but he studied also in master in astrophysics at Princeton University, and then the PhD at the Johns Hopkins University, also in the United States. So Luis Felipe is a really worldwide expert in nuclear fusion diagnostic, and he's leading different experiments in the United States, but also in China, in France, and in Japan. He's currently the head of the advanced project at Princeton Plasma Physics Laboratory. So in May, he was on the news for a record that they got in Tokamak West, which is in France. And since I knew he was coming for a conference in Salamanca, I think at CLPU, so I invited him. So I think it will be important to hear from him about this important achievement about Tokamak. So I'll leave you.
Thank you, Julian.
Thank you for coming.
Yeah, thank you. So it's a pleasure to be here. Thanks very much for inviting me to allow me to come here. But it's not an invite, because I do have the personal interest of working with CSIC and CNM in particular, because we are very eager to find new ways of making measurements. Currently, we do measurements in machines which are very large, larger than this room, and are very comfortable using silicon detectors, the same as I have in my phone, okay? But I am gonna put these detectors next to an environment like what you have in the screen, next to the sun. And of course, they won't survive. So you have two large constraints. You have the temperature, which can be of the order of hundreds of degrees temperature. And you have also a lot of radiation, which could be neutrons and could be a sea of gammas, okay? So the picture on the screen can actually, or the movie in the screen is showing you a lot of different mechanisms going on in the sun, can actually explain this whole talk, because we can talk about energy, we can explain about the fusion processes in the sun, which we are trying to do the same fusion on the sun here in our backyard. We want to have novel X-ray cameras so we can do physics and measure not only weird time-varying phenomena like what we call MHD, magnetohydrodynamics, or we can measure plasma properties, densities, temperatures, velocities, etc., etc., etc. And then, of course, my urgent call, mi llamada urgente, the fact that we need your detectors, your CNM detectors. We are trying to do fusion, but you guys have tens of years of experience working with high energy physics experiments, which I don't have. So instead of reinventing the wheel, I want to come here to ask for help, okay? And this is exactly what we're doing here. I'm not here to talk about necessarily how good of a friend Julio is, and how he knows my family and I know his family, but I need your detectors, okay? So whether we go, hola, ¿cómo estás? Qué bueno verlo de nuevo.
Sí.
So apart from visiting old friends, I really need your detectors, not only for photons, but also for particles, in this case for neutrons. So in my attempt to, let's see if it works. In my attempt to basically talk a bit about, or give a bit of background, the image on the screen is an image from a satellite that basically tells you the parts of the world that have light and the parts of the world which doesn't have light. And it's clear for many people that, at least from a humble perspective for me, that energy is the great engine that moves the world and is basically at the heart of development. So if you want to look at communities that are in dark, having development in those communities is extremely challenging. It's extremely challenging that without energy, people will not basically reduce poverty. Energy is actually the engine that drives innovation and drives industries, which eventually build the private sectors to actually reduce poverty. And most importantly, in a year or two from ago, we understood more and more, especially here in Europe, the dynamics of energy in terms of creating or avoiding geopolitical conflicts, for example, in what's happening now between Russia and neighboring countries, okay? So energy is actually extremely important, and more important so in the last couple of 100 years. In the picture on the screen, you see a history of nearly 200 years, and you see this carrera exponencial, this exponential run to for energy consumption. And whether you want to consider biofuels, oil, or hydropower or nuclear power, the take-home message today for you is we are in this race in the sense of spending lots of energy, which is proportional to the amount of people in the world. Yes, of course, okay? We are increasing the amount of people in the world. We used to be only 1 or 2 billion. Now we are in the realm of 7 to 8 billion people in the world. But the rate that we have spending more kilowatt hours per day is also increasing. Okay, and the point is, countries that have basically the same sort of resources, and maybe neighboring countries could have very different portfolios of energy. In the screen, you see a very interesting example of data that I actually gathered less than a month ago. These are annual consumptions of energy for 2 neighboring countries, France in the left and Germany on the right. And you have, roughly speaking, the same amount of people, you know, 68, okay, let's round the number, 70 million for French, 80 million people for Germans. The consequences of having a very different portion of the pie of how they distribute their energy consumption is striking. The French produce only 53 grams of CO2 equivalent per kilowatt hour. The Germans, with the current decision of turning off the nuclear power plants, now produce nearly a factor of 10 in terms of grams per CO2 per kilowatt hour. It's quite striking. Okay. So we're trying to find new ways of producing energy. This exponential curve that I showed before is producing this amount of CO2 emission. The graph in your left is basically the last 50 to 60 years, and it's clearly an exponential growth of CO2 production in the world. And the second take-home message that I'm trying to give you is, how do we turn from the situation in the left to a situation in which we look for a more green solution, okay? And this is the challenge that we have all around the world. And the thing is, how do we pick the right technology? How did Spaniards here in Spain decide to pick the right technology? You can pick nuclear, geothermal, natural gas, hydroelectric power, burn some coal, use some wind, or use some solar. Every single country has a different ratio. But what is very important is to understand what is this plant capacity, el factor de planta, for each particular solution. Solar, which is really strong in Spain, and wind, which is also strong in some parts of northern Spain, have only solar plant capacities of the order of 20, 30, 40%. In Peru, for example, in the south of Peru, where we have near Chile, the Desierto de Atacama, and the south of Peru, we have very, very good solar power with capacity plants of the order of nearly 35%. Wind, also in the south of my country, in the north of Chile, or even the south of Chile in South America, close to 50%, maybe, okay, pushing the limits. But how do you get 100%? Well, you get 100% if you go to more like solutions with geothermal or more nuclear. And then is when I want to tell you about this nuclear option that the French actually use very well, and some countries want to use too. But how do we generate and benefit from nuclear power? And this is quite simple to understand. In every single nuclear reaction, you have an initial state or a start, and then a final state at the end. And then, of course, the energy is just simply the variation of mass multiplied by c squared. C is a very, very large number, okay? 3×10⁸ meters per second. C squared, it will be 9×10⁻16. Okay, 9 is another 10. So it's 17 zeros, 17 ceros, next to the variation of mass in the reaction. So even if the reaction produces a mass difference which is extremely small, you have 17 zeros in that multiplication to understand how strong nuclear power can be, okay? So there are two ways of dealing with nuclear power. One is nuclear fission, in which what we do is we just bring up a big knife, let's call it a neutron, and we cut the cake, we separate the cake into smaller pieces, and we cut high Z materials, and I put 3 there. Uranium, plutonium, and thorium are examples currently in the world. You come up with a neutron, you impact the neutron in this objective, and you produce 2 separate pieces of cake and also more neutrons. That will impact another piece of cake, produce more neutrons, and then you have a reacción en cadena, a chain reaction. Okay. Now, we do have to deal, at least in my piece of the world, with a negative impact of what humans, we, have done in the past, okay? We cannot forget, especially after a year when Oppenheimer won all these awards and the movie was fantastic, we do have to remember what happened in Fukushima, in Hiroshima and Nagasaki, and then the disaster in Chernobyl, and lately some bad design by the Japanese causing the Fukushima disaster, okay? Because it was a bad design. If they would have heard the recommendations from the International Atomic Energy Agency, nothing would have happened in Fukushima in terms of the nuclear disaster, okay? But we have to accept also that there is a loving relationship between a lot of different countries, and France is a beautiful example, in which case they use 70% of the whole electric power from nuclear. And you will see actually how smartly they spread some of the reactors around the borders, okay? So they actually are exporting electricity, okay? So it's not only using electricity, but also exporting electricity. My solution is completely the opposite. While fission is breaking the cake, I want to unite, I want to blend very light elements. And in fusion, what we need to do is we need to fuse hydrogen, which is the lightest element from water, okay? So in my case, I grab a couple of cousins of hydrogen, isotopes of hydrogen, called deuterium and tritium. Deuterium has 1 neutron, and then the proton. Tritium has the 1 proton, but 2 neutrons. And from the blend, from the mix of deuterium and tritium, I produce energy. I produce a helium, an alpha particle, okay? And I produce a neutron. Well, nothing stops the neutron. Maybe something will stop the helium, but nothing stops the neutron. So the neutron basically is gonna go through a piece of water like this one by reactions with water, we stop the neutron, heat up the water, and then produce electricity by moving some helical part, like a conventional way of moving an engine, okay? Now, of course, there are several complications of this. This is not as easy as Luis showing you a glass of water, but I'm trying to explain this in a very simple way. So in summary, you have to go home understanding that fission is simply cutting a big atom like uranium-235, producing a lot of reactants, while fusion is, by cutting this very heavy element, And fusion is a very distinct process. You don't cut anything, you bring together very light elements. So nuclear fusion is indeed a very nice alternative to the world energy challenge. The challenge also for me is that we require a very hot plasma, okay? An extremely hot plasma. And you may have that question of, well, okay, what is a hot plasma? In this picture that you have in the screen that we took with some friends in the United States, you have actually a very nice formation of some geothermal bath, and you see 3 states of matter. And all our kids learn in school solid, liquid, and gas. And in that picture, you see snow, you see water, and you see vapor. Okay, so you do have the 3 states of matter in that screen. Well, there's a 4th one missing. That one. That is a plasma. In nature, a plasma only occurs on Earth when you have lightning storms. The channel, this particular channel of gas that has been ionized at a very high voltage and a very high current, is not gas anymore. Here, the electrical conditions of this scenario has separated charges and have taken the positive charges in one direction and the negative charges in the other direction. That little channel where current flows is no longer a gas, it is a plasma. So basically what the difference between the 3 typical states of matter that we have on Earth and the plasma is literally only temperature. On Earth, solid, liquid, and gas will be between -10 degrees and plus hundreds of degrees. But plasmas are in the order of thousands to million degrees. And by the way, 99% of the universe is a plasma. Oh, I'm missing an S here. Okay. So when you look up in the sky, there's nobody turning on the nuclear power plant in the sky, in the stars. Every single star or light that you see in the universe comes from most probably a nuclear fusion reaction and plasmas getting ionized and getting also recombined. So why so hot? Why do we need fusion at really those infernal temperatures? Okay. Well, we need fusion at those temperatures because, let's do a bit of physics. We need a cross section. We need a cross section to be in a matching condition with energy because of one very simple argument. When I try to fuse 2 hydrogens, I strip the electrons. Okay? I create a plasma. I take up the electron from the water and I only get protons. And from the protons, if I want to bring 2 protons together, I need to face the repulsion of 2 positive charges. It's really simple to see. When you want to bring those together and make them fuse, they're going to try, the Coulomb force is going to rip them apart. Well, the only way to overcome that force is to give them energy, okay? To make them get closer with more energy. More energy, they're going to get out. Well, give them more energy, and then they finally might fuse. The cross-section for my reaction of interest here of deuterium-tritium maximizes at 20 kiloelectron volts. 1 electron volt is 11,000 degrees. So we're talking about this peak of deuterium-tritium is in the order of 20 or 30 million degrees. Now, when you compound this cross-section with a Maxwellian distribution function, you may move that peak closer to 10. Okay, so at least we need 10 keV. 10 keV is 100 million degrees. Okay. Now, it's difficult for the public, and especially for politicians in the States or in Peru or in Spain, see, 100 million. I'd have my coffee at 100 degrees, and you want 100 million. It is difficult to understand. Some people think it's fascinating, but what is also difficult is, how do we measure that? And that's another reason why I'm here with you, because I want to work with you on this project. Now, one little caveat, okay? I need to be quite honest here. So I begin with a reaction of deuterium and tritium. Okay, deuterium in the left, tritium in the right. I have a fusion reaction and I have an alpha particle and then a neutron. So far, so good. I told you that story. What am I missing? The alpha particle is a particle that is ionized, okay, has a positive charge. And the positive charge can actually re-enter the reaction and transfer energy either to the deuterium, the tritium, or the electrons around. What do we do with a fast neutron? Okay, which we'll talk about neutrons because I want your help also to measure the neutrons, flux and spectra. What do we do with the neutron? The neutron, I told you, will heat up the water. Now, the neutron has one more role too, one more. There's not enough tritium in the world. Tritium is not natural, okay? Tritium is not natural. Deuterium is. For every 10 atoms of hydrogen, 1 is deuterium. But tritium is not natural. So we get it from the CANDU reactors in Canada or some other reactors. Now, there's a way to produce tritium, and that is we grab the neutron and we put a blanket, una sábana de litio, a lithium blanket. Okay, our Argentinian friend here might know that in Argentina and Chile and Bolivia and a little bit of the south of Peru, we have a little bit of so-called triangle of a bit of a quadrilateral of lithium in the world. 80% of the lithium in the world is where Martina and I are from. Okay, so we want to also go together with many people from our community to South America to tell them, well, you need to begin thinking of selling lithium to these fusion nerds that want to sort of solve the energy problem. Okay, the reaction that we want to look for is a lithium with a neutron. Okay, we'll give you a tritium. We'll give you an alpha particle too, but we'll give you a tritium. There's some reactions which are exothermic and some reactions which are endothermic. So that's why we prefer lithium-6. In nature, lithium is separated between lithium-6 and lithium-7. If I'm not mistaken, or 90% is actually lithium-7, the lithium that we don't want. So chemically, if there's anybody here interested in these problems, it is extremely interested to think how we do separate lithium-6 from lithium-7. This is one of the challenges that we have not solved yet, okay? But we do need lithium for tritium replenishment inside the machine, okay? So keep that in mind. So we want to create fusion like in the sun. So there are 2 types of fusion that you need to remember, okay? Very easy. One called inertial, that uses lasers, like this one, maybe a little bit more powerful than this one. And one called magnetic, it's the one I would work with use magnets, okay? And I want to try to explain in a very simple way what's the difference between one and the other. The inertial creates and focuses laser power on a little pellet like this one. This pellet has inside a frozen deuterium-tritium mix, okay? So there are 2 directions here, one direct and one indirect. The direct one is when you have 192 lasers on this tiny spot. And then you ablate the surface of this polymer, and then you begin to warm up the deuterium-tritium mix, and then you warm it up, you boil it, you make a plasma, you ionize, you keep warming, you compress it, and then you create a tiny nuclear bomb, okay? It's an uncontrolled process. This is funded by the United States National Security Administration, National Nuclear Security Administration, NNSA, okay? It's an amazing piece of machine. There's also an indirect way that tends to be slightly more efficient, because if you assume a little pebble and 192 lasers, there's a little bit of bubbles that you form inside this capsule that we call Rayleigh-Taylor instabilities, regiones de alta densidad y baja densidad, que hay mucha turbulencia y el calor no es uniforme, ¿no? So they created a second technique, a technique in which you point the 192 lasers into this gold capsule. It's called indirect drive. the lasers will melt the gold, will ionize the gold, and you create a more uniform way to compress the capsule, okay, to avoid the Rayleigh-Taylor density instabilities, okay? So there are two ways, okay? The direct way and the indirect way. And here, I have to accept that they beat us. They beat me, okay? Me ganaron el partido. ¿Por qué? Porque they already did 2 years and last year and this year shots of ignition. What means ignition? They put 1 watt, they got 3 watts. Okay, remember, that's Einstein's equation. They got 1 watt, they got 3. By the way, they can go up to 100 watts, but it's not that efficient yet. Things are happening, okay? But they beat me. Me han ganado, ya van 3-0, okay? Okay, the fields producing lasers are similar to 2 Olympic stadiums here in Barcelona, okay? Full with lasers of high power. A very big ball, you see a worker here with tons of holes for diagnostics, looks like a Swiss cheese, where you put the 192 lasers and you put also diagnostics to measure the plasma, okay? And they got ignition at the National Ignition Facility at the Lawrence Livermore National Lab in the US. Now, I am a little bit critical of this 3-0. Why? Because they did it only for a few picoseconds. Few picoseconds. Like this. That's it. And 6 months later, another picosecond. Es un poco ridículo, ¿no? O sea, if I want to solve the energy problem in the world, these lights, and if any of you have kids or the 2 daughters that my friend has here, the chicas at home spend energy 24/7, non-stop. A picosecond, whether they can scale a picosecond to real time, to uniform 24/7, or maybe to a hertz, multiply in your head the number of scales from 1 picosecond, 10 to the minus 12, to 1 hertz. But they beat me. They are 3-0, okay? My solution is a little bit different. When you create a plasma and you have electrical charges respond to the Lorentz force. The Lorentz force is nothing but Q times the electric field and Q times V cross B, okay? That is the force that we are using to create a plasma in a donut-shaped machine called a tokamak. When that donut is uniform, we create what the Russians invented and the Americans invented, called as the tokamak. When that field is a bit non-homogeneous, imagínense un sacacorcho para abrir el vino. The sacacorcho is helicoidal. When that helical distortion can also confine a plasma in a machines that they have in the US, in Japan, and in Germany called a stellarator, okay? Stellar is star, is a machine that makes a star, okay? But the geometry is not homogeneous. It's a bit 3-dimensional. It's a bit more complicated, okay? So I am using just the Lorentz force to make sure that particles can flow around a magnetic field in the gyro frequency motion, okay? I bend the magnetic field in some sort of ring-shaped fashion along a donut or along an apple and just simply move the charges. With radio frequency heating, I produce the jam, la mermelada de en medio, is a hot part of the plasma. Why I need to do that? Because I cannot have the plasma touching the walls. If the plasma touches the walls, it will melt the walls, okay? So I literally levitate the plasma inside this containment, okay? Now, ideally, the plasma touches the walls and produces something called sputtering. If the walls are made out of carbon, carbon will go inside, and we can do spectroscopy on carbon lines. If the machine is made out of molybdenum or tungsten would also flow inside, and I can do spectroscopy on molybdenum and tungsten lines to understand what the plasma is made out of and certain characteristics of the plasma. So I create this bottle, this containment device full of magnets, with a toroidal magnetic field, and also produce, yo le llamo, cuando hablo con mi familia, una especie de licuadora portátil with magnets everywhere that produce magnets in 3D, in a 3D fashion. And I use Maxwell's equations to basically, for example, create the plasma. The plasma carries a current. When the plasma carries this current in red, the plasma also creates another field that we call a poloidal field. So the combination of the toroidal field of the poloidal field is a helical field, como el sacacorcho, that wraps around the machine and confines the plasma, so the plasma doesn't touch the wall. Okay. These are some an example of the two machines that I have worked in Oxford and in MIT. This was funded by the United Kingdom Atomic Energy Agency, and this was funded by the Department of Energy. These are some of the tiles in the wall that I was just showing you, made out of beryllium and tungsten. And in MIT, we actually work with molybdenum plasma phasing components, or an alloy called TZM that is 99% molybdenum. Okay. Now, funny, you're gonna see a very nice characteristic of these machines. This parrillas. How do you say parrilla? Parrilla también en español aquí, ¿no? Yeah, como la parrilla para hacer un asado, ¿no? But these parrillas, okay, are nothing but radio frequency tools. Okay, the same way you heat up the microwave in your house, the water, well, I put megawatts of power here. Your microwave might have maybe 1 kilowatt. I put several tens of megawatts of power to do electron cyclotron heating or ion cyclotron heating. Okay, and I'm gonna step there so we don't discuss more plasma physics. This is a machine that I work in the south of France, very close to here that Julio just made that comment where we got the second record. Okay, this is a machine in France which was pretty old. It's nearly 30 years old. The French actually decided to change the walls, this wall that I was talking to you about, those tiles, from carbon to tungsten. Okay, why? Because then carbon melts when it's really hot. Carbon tends to melt. And one other problem, carbon tends to absorb the hydrogen in your reaction, and you don't have normal density control. If you have a sponge in the wall absorbing the hydrogen, you also create a license with a radiation. You break a radiation license, and you need to be careful with that. So they changed the wall to tungsten. Now there's one problem. Tungsten, if a tiny piece of tungsten falls in, the whole plasma collapses. Why? Carbon has a charge of 6. Tungsten has a charge of 74. Let's make some numbers. 74 divided by 6, roughly speaking, 10. The radiated power of tungsten, or the radiated power of any element, doesn't depend on z squared, that the electric charge, depends on z to the 4th. So 10 times more charge would imply 10,000 times more power, okay, per atom. So one tiny piece of tungsten falls in, you're dead. So it's extremely challenging. But the French just did it, and that's how we broke the record. We have a machine of 3.7 Teslas. Coincidentally, they use superconducting machines, magnets, and they actually cool the magnet to minus 271 degrees. Minus 271 degrees, nearly the coolest temperature of the universe. 10 centimeters later, we reach 50 to 60 million degrees. Again, minus nearly 0 Kelvin to then millions of degrees. So this was quite amazing. There's a power of 15 megawatts. Remember the megawatts that I was talking about, the parrilla, the radio frequency heating. The plasma temperature could reach nearly 100 million, and the plasma duration will be only 1,000 seconds. Why? Because we'll break some heating limits of this particular very old machine. But nonetheless, we achieved this record. How did we measure this record? Well, these are more details of how we are testing tungsten materials inside this reactor, and how they cover the reactor with a lot of different components of tungsten or tungsten alloys. And this is another example of a worker working inside a machine. And when we don't allow workers inside the machine, well, we'll send robots too, to be able to see things, okay, with manipulating arms that go inside the vacuum. But how do we make the measurements? Well, we make the measurements using X-rays. I am an X-ray junkie. Yo soy un adicto a los rayos X. Every time we talk with Julia about that, we talk about rayos X all the time. Why rayos X? Why X-rays? Because an important part of the power is lost as radiation. And maybe up to 90% of that radiation is in the X-ray form. And it's a very simple exercise. Try to equate the energy of the photons scaling with the electron temperature. Very simple. H nu or Hc over lambda scaling with Te, with the electron temperature. And for thermal plasmas, you'll be in the X-rays. And for non-thermal electrons, you'll be in the hard X-ray range. So it's very simple. The only way to see a plasma is through X-rays. You put your eye in a reactor, you will see only light in the boundary, okay? En la pared. Luz visible va a haber solamente en la pared because of recombination. The meat, the sauce of the plasma, it emits only X-rays. So hence, I need to work with designing hard X-rays and soft X-ray cameras. That's my business, okay? And I need those cameras to survive a lot of difficult environments. So the measurements of this radiated power in the X-ray range enables a characterization of a lot of parameters, plasma emissivity, or sometimes also radiated power, measurement of electron densities, impurity densities, electron temperatures, impurity temperatures, velocities, et cetera, et cetera, et cetera. There's a bunch of parameters that we sit very comfortably in our control room, and the X-rays measure these quantities, okay? This is, for example, how I did it maybe 12, 13 years ago. When I was at MIT, we had the plasma in this containment device. This is a cross-section of the plasma. These are two fans. Here, there were 58 detectors in this direction and 58 detectors in this direction. So it's exactly like you going to the hospital and this being your leg and somebody X-raying your leg, okay? In this particular case, the X-rays are emitted by the plasma. In the hospital, there's an X-ray tube that emits X-rays, goes through your bones, and there's a plate here to detect the X-rays. In the case of the plasma, it's different. The plasma emits its own X-rays, okay? And I can see how the plasma can move from a circular shape to a bit of a displaced core to maybe create a kink, to maybe create this subtle thing, crescent moon croissant, okay, which is an instability. So it allows me to study plasma instabilities. What's here? The X-ray detectors. Detectors en modo corriente, es decir, yo mido una corriente en microamperios. Pongo un amplificador de corriente de 10 a la 6 voltios por amperio, y for each microamp, I measure 1 watt. In modo corriente, that means I measure all the power that comes from the plasma, okay? There's an efficiency of 0.1 to 0.3 amps per watt for each particular amp. For each particular watt of power, I measure a particular amp of current. And again, I put a transimpedance amplifier in current mode, and I digitize the signals. And of course, everything has to be exquisitely calibrated in order to do tomography, okay? These are not line integrated. I can show you also line integrated images, because you line integrate along with the cord. Well, you'd have to do a tomographic inversion to be able to get these pictures. So you study magnetohydrodynamics, or you study, for example, how impurities are transported in the plasma also. Very pretty pictures. Now here, no plasma parameters. Where's the density? Where's the temperature? Where's the impurity? Where's the velocity? Nothing. With these measurements, You only measure power, potencia radiada. Y por ende, no mido ninguna característica del plasma interna, densidad, temperatura, velocidad, etcétera, nada. Pero hago unas figuras mostras y los papers están aceptados, ¿no? Entonces, it's very, very nice. But I am greedy. Yo quiero más, ¿no? Entonces, we have just come up with a new technique on how to get light from the plasma and get measured properties. Déjenme enseñarles dos espectros. Imagínense que yo tiro un pedazo de silicón o un pedazo de argón al plasma, ¿ok? You see lights from silicon, you see line emission from silicon, you see line emission from argon, and you see a continuum. What are these colors? Colors is the temperature. Depending if your plasma is cold, 0.1, or your plasma is hot, 10 keV, 10 keV is 100 million degrees. The energy dependence is different. This slope, esta pendiente, depende solamente de la temperatura del plasma, ¿ok? Entonces, si yo puedo medir la dependencia de energía, I can measure the temperature from the slope. ¿Se dan cuenta? Now, if I want to focus on these lines, I do what we call Doppler spectroscopy. Para hacer espectroscopía Doppler, necesito un cristal para hacer la difracción de rayos X. I need a crystal. The same ways when you look at a prism and you diffract visible light, well, I will need an X-ray crystal, and I will need the Bragg law to basically diffract X-rays to the Bragg angle and measure a specific line. There are hundreds of lines here, but I need to look at one line, maybe the strongest one, to do Doppler width for temperature, Doppler shift for velocities, and Doppler intensity for the impurity density of the plasma. Okay, but these sort of detectors plus some X-ray crystals help me to see the lines. But I don't want to talk about that. Maybe that can be another talk and next time I come. Now I want to focus on what we just did recently that Julio was mentioning of the record shot. We focus on the continuum. It's easy. You need less resolution, okay? Because for here, you need high energy resolution to resolve a line, one. For this section, simple. You just measure the slope of the continuum and you get the value of the electron temperature, okay? Now, Julio knows this, we had a very nice collaboration with a company in Switzerland called Detectors, which stem from the Paul Scherrer Institute in Switzerland, okay? Now, we have these cameras and Detectors allows us to go inside their laboratories. Why? Because we promised to make measurements of impurity density, of temperature, and so many different plasma parameters. They told us, okay, Luis, come inside, play with our electronics, and try to do something. I want to also get deeper in a bit of the challenges that we have. I mentioned a couple of cases of silicon and argon in the previous slides. Well, listen, I put here very different elements: hydrogen, carbon, oxygen, aluminum, silicon, argon, calcium, iron, nickel, molybdenum, and finally the nightmare tungsten. Each element has a particular spectrum. If a little piece of each element goes inside the plasma, you would emit this kind of light. You would emit a certain amount of photons per centimeter cube per second. This is in logarithmic scale as a function of the photon energy, as a function of the plasma temperature, okay? So there's a Z challenge. Geez, what element I'm gonna use, okay? What kind of spectroscopy I will do? Now, I need to resolve the photon energy, okay? This axis here. Now, here comes a nightmare. And here is why I'm here with you, because I am swimming in measurements in a pool full of neutrons. Desgraciadamente, la fusión me produce tantos neutrones que tengo mucho ruido. For each neutron, por cada neutrón, tengo varios gamas también. Viene un neutrón a impactar y produzco muchísimos gammas. Well, how do I deal with them? Es un dolor de cabeza. Tengo electromagnetic noise. And for many of these, I want to go in vacuum. And I already told Julio, I haven't even put here, ¿qué pasó with the temperature? You can have temperatures at room temperature, but you can have temperatures at hundreds of degrees. Hence, why I want to use silicon carbide, correct? I don't want to use silicon. I need to move to use silicon carbide or use diamond or use maybe gallium nitride or et cetera, et cetera, et cetera. Okay. And then also, for example, the problems of magnetic fields. I'm putting these detectors in a region that has high magnetic fields to confine the plasma. So I partner with this company in Switzerland called Detectors, like I was mentioning before, wonderful detectors. They work in this hybrid mode in which you have an X-ray getting to a silicon lattice. In a silicon lattice, you produce a photoelectron cloud of electrons and holes, okay? And basically, you have a lot of electronics underneath each particular pixel. And this is what we play with. And we have these cameras in very small fashion and very large formats as well. And this is one of the cameras that I installed actually in China to do X-ray crystal spectroscopy. Now, what did we do? We play with the electronics underneath each pixel. Here comes the signal. Here's the bump pad for each particular pixel. When the signal is received, I have a charge sensitive amplifier, CSA. Okay, so I measure the charge that photon generates. And I have a comparator system. What the comparator does is, okay, if I put a threshold at 3 keV, si pongo un threshold a 3 keV y le pregunto, ¿no? ¿Cuántos fotones tienen energía superior a 3? Y los va contando. Si la energía es inferior a 3, no los cuenta. Entonces, empiezo a tener una especie de discriminación por energía. Now I have energy resolution. Okay, I do a calibration using 28 fluorescence targets in rayos X, desde low energy of 2, 3, 4 keV up to maybe 20 keV. For silicon, I do low energy. For cadmium telluride, I do energies up to 100 keV using a uranium source. And what I end up with is these curves. I can manually change, like an old 60s, 70s radio, tune the energy using these electronics, and I can produce these curves that I even have a complementary error function describing really well the energy sensitivity of each. When I did my thesis nearly 15, 20 years ago, I dealt with filters, with beryllium filters, like Julio is dealing now with aluminum in the tungsten tube downstairs, okay? When you deal with different thicknesses, you begin to destroy the energy resolution. Here, I have a very constant energy resolution from low energy to high energy. And this is how I did that. And we construct these cameras, okay? We had a couple of postdocs working with us in the south of France. Here you see them inside the reactor, basically doing the spatial calibration of all these cameras. We install a system called multi-energy soft X-ray. We install another one on top called multi-energy hard X-ray. The difference is that this one in the bottom had a silicon detector. The one in the top had a cadmium telluride detector for low energy and high energy. And we create a very simple pinhole camera arrangement. There's a little hole here of the order of 2 millimeters, okay, that allows the X-rays from the bottom to go up and the X-rays from the top to go down on the camera. And this is the Pilatus camera that we put in the machine. And this is how stable the current and the plasma parameters are. And what we did, we actually obtained the raw line integrated, el perfil integrado, okay, en una línea de integración espacial along many channels in many different energy ranges. Then the next step is we did a tomographic reconstruction. Okay? Si este es el eje magnético, pues se hace una especie de inversión de Abel okay, in case the plasmas are circular. When the plasmas are a bit more elongated, you need to do a bit more mathematics, okay? But it's nothing but an inversion from here to here. And the inversion reach really nice signal to noise ratio for a lot of different energy ranges. And then is what happened. If you plot those intensities as a function of thresholds, and you actually have a model to explain what happens with 1, 2, 3, 4, but whatever temperature, the temperature of this location in the plasma was of the order of 50 million degrees and lasted for 6 minutes, 364 seconds. I went to a machine to have a coffee and came back, and the plasma was still at 50 million degrees. When I did my PhD thesis, I did something similar only in 2 seconds. Jumping from 2 seconds to 6 minutes was really, for me, an incredible pipe dream. Okay, so we were extremely happy. Now, why did we stop at 6 minutes? Well, at the end of one of the pipes in the reactor, there was a Kapton cable. And there were few electrons being lost in the plasma, burning the Kapton cable. They burned the Kapton cable, and that gas entered the plasma, created a rise in density that the plasma control system couldn't take, and then the plasma shut down by itself. Okay. Now, they are installing all sort of equipment now to protect all the Kapton cables in the machine, and we hopefully by December we will reach 1,000 seconds. Now, what is next? And here is why I'm here. We need to develop, maybe not develop, we need to use all your solutions, because you do have way more experience than myself on dealing with radiation, hardened sensors, and electronics. And now, as I was telling to Julio and others in the room, now we have the Department of Energy, the private sector, and universities interested in solving this, okay? Now, what is our main issues? We need to circumvent the gamma, the neutron-induced noise, the temperature and magnetic field limitations, as well as the lifetime of these detectors. Here, there's a map of another detector, of another reactor that we're building in the south of France called ITER. Maybe you heard about ITER. By the way, ITER 2 days ago got delayed 10 years. Okay, so it's another $10 billion for the world to cough for ITER. Whether that's going to go through, we don't know. But nonetheless, you have fluxes. I was telling Martin the other day, fluxes of the order of 10 to the 18 to 10 to the 20, depending on the power, neutrons per second. Neutrons per second. Now, hold on. The figure of merit that I learned from you is neutron per centimeter square of a neutron equivalent to 1 MeV, correct? Well, the idea that we all have is let's put the neutron detectors far away, and you consider 1/4 pi r square as a way to attenuate the amount of neutrons, okay, neutron fluxes. But nonetheless, we need to run away from using silicon detectors, okay? We have developed so much technology with silicon, and none of them will be able to use in these reactors. So because of neutron damage and the survivability at high temperatures. So this is why I'm here, because you do have a lot of experience dealing with materials possibly being used in high luminosity experiments at CERN up to maybe 10 to the 17 neutron equivalents per centimeter squared. Julio told me today that somebody wants to try to use things at 10 to the 18 in neutron equivalents. So we'll see. So my message is very simple. We need to find synergies between the fusion energy sciences, FES, and the high energy physics community that have much more experience than us dealing with these detectors. I put here a sentence that I actually copied from one of your reports from the old RD50 collaboration, Julio, that eventually promised nearly 10 to the 16 by 2024, 2026. And that eventually by 2030, somewhere in the order of 7 to maybe 10 to the 17 to 10 to the 18. So we are aiming at 10 to the 16. If I can demonstrate in the next 4 years with the money I'm going to get from the government that we can propose solutions that take to that 16, people will be extremely happy, okay? Julio was showing me yesterday and today some detectors that he irradiated maybe 1 10 to the 15 max. Well, if we can go to the 10 to the 16, great. We need to compare part of my project now that I'm applying for money now as we speak. We need to compare the regular silicon to other configurations, and you do have a lot of experience dealing with 3D detectors, maybe with some enrichment techniques as well, or other materials. I am interested in testing silicon versus diamond, diamond with nitrogen, diamond without nitrogen, silicon carbide, gallium nitride, aluminum nitride, gallium and aluminum nitride, and all of this also for high temperature applications. And a lot of different measurements that we can do in the plasma of radiated power, ultraviolet, low to high X-rays energies, and also, by the way, I was talking to Martin, neutrons. Neutrons need to be measured. If we don't measure neutrons, we know nothing about how much power do we have. And with neutrons, we need to specify two things. We need neutron flux, neutrons per second, and we need neutron spectra. So for neutron spectra, we were thinking using diamond. Diamond, and with Julio, we want to also use silicon carbide for neutron spectra, for this carbon-12 line, okay, around 8 MeV. For 2.5 MeV, things are much more complicated in terms of getting spectra, okay? So I was showing Martin and others some research made by the Italians on the possibility of getting DD 2.5 MeV neutron spectra from using a click scintillator made out of chlorine and lithium. And of course, for other applications of lower energy like UV and X-ray spectroscopy, we were also considering with Julio the possibility of doing LGAD detectors. So in summary, whether I design things in current mode, like these tomography systems, or in pulsite mode for Doppler spectrometers, or in pulsite mode for this multi-energy concept we just developed and tested in France, we need detectors, okay? We need detectors that can help us do a lot of spectroscopy for tungsten. In the future, every single machine in the world will have plasma-facing components in the wall. A significant fraction of the power delivered for each watt, por cada watt que le ponga el plasma va a radiar energía en forma de fotones. Bueno, me puedo sentar en el control room a medir esos fotones, okay? I want to measure those photons. Modern diagnostics in the X-ray range would allow us to probe very different parameters. We need better neutron monitors for DD and DT. For DD, 2.5 MeV. For DT, 14.1 MeV. Flux, and especially spectra, okay? Energy spectra. And therefore, we need urgently need for radiation hardened sensors for our communities. Muchas gracias por su atención.
Thank you, Luis, for this very interesting talk. Questions? I hope to convince you that you can really the future for
Es un poco complicada la charla, pero en castellano. Primero agradecerte la charla, es muy interesante. Para ello tengo que suponer que la he entendido, y esto me ha costado. Pero bueno, está muy bien. Mi pregunta es un poco, como desconozco todo este mundo, ¿no? Claro, si calentáis algo a esa temperatura tan alta que claro, yo cuando estudiaba teníamos la conducción, la radiación y la convección. Convección, entiendo que estas cosas están hechas a la vacío.
Sí.
Pero la conducción, o eso le evita, o con esas temperaturas, cualquier objeto que esté conectado físicamente a otro, no sé si esto que hacéis está levitando, pero en un modelo real tuviera que generar mucho, eso tendría que estar aguantado de alguna manera, porque si tiene conducción, ahí se te van a ir muchísimo energía, ¿no? ¿Esto cómo se soluciona o no te planteo?
Mira, para seguir en español, la idea clásica es que todo esto flote, ¿no? En el caso inercial que mencionaba al comienzo, porque acuérdate que hay dos formas de fusión, ¿no? Una es inercial y la otra es magnética. ¿Te acuerdas de estos dos casos? ¿No?
Sí.
En el lado inercial, no les importa. Porque claro, agarra una pepita y le tiran 200 láser y hacen literalmente una explosión nuclear. El mundo y los Estados Unidos firmaron hace ya una década o más de una década, una norma para no hacer más explosiones nucleares. Entonces los gringos dijeron, muy bien, hagamos un experimento de fusión. Pues literalmente hacen una mini o una microexplosión nuclear con estas cosas, ¿no? Y testean modelos. ¿Okay? Hay alguna gente que, por ejemplo, yo no puedo entrar a revisar ciertos modelos nucleares porque hay experimentos de física nuclear para desarrollo de bombas en el futuro. Y yo no toco ese tema. ¿Okay? Y además no me interesa el lado inercial. Pero en el lado inercial no hay conducción, convección, nada. Ellos tiran los láseres y revienta todo, ¿no? Sacar energía para darle energía al mundo de esa forma a mí me parece un poco así como que extravagante. Entonces, mi forma, esta forma que te contaba yo a ti, o a ustedes, es hacer que el plasma levite. El plasma no toca la pared. Sin embargo, tengo que ser más honesto y decirte que algunos modos de confinamiento involucran que yo tenga una solución para hacer power exhaust, para que el calor se vaya, ¿no? Y la sección transversal es de esta forma. Ya no es totalmente esférica en el caso de que Luis Felipe flote el plasma perfectamente, ¿no? Ya acá hay también conducción térmica. Y acá hay unos platos que se llaman divertores, que supuestamente te reducen la cantidad de potencia por unidad de área para cada elemento, ¿no? Entonces, hay unos trucos que hoy en día usamos, usando también litio líquido para evitar que hayan solamente puntos de calor, y no puntos, sino ya superficies de calor. Entonces, sí, número uno, el plasma está levitado. Y número dos, sí hay condiciones en las cuales estas patas también transfieren calor al sistema. Y ahí hay otras soluciones. Pero eso se llama Plasma Material Interactions, que es un poquito más complicado de tratar acá. Pero eso es una buena pregunta, sí. Gracias.
Well, I had two. One was on this inertial laser. What you said, but it's really only for military application or for theoretical study, because I never understood how they can produce.
Well, there are two companies now, Julio, in the US and one in Europe, in Bordeaux, which are trying to make this a reality for a company. Okay. And what they do is they create also a beam of electrons, one, another company, a beam of protons to assist in the reaction. My problem is that we are jumping to possible solutions, but still on the timescale of a picosecond. Try to scale something from a picosecond to Julio. They wanted 100 hertz, huh? 100 hertz. Imagine a jump from a picosecond to a hertz, to a second. Hay 12 órdenes de magnitud. O sea, el crecimiento es alucinante. And the problem is not physics. The problem is more engineering. How you engineer a little pellet to come exactly from the heavens and go exactly to the center of mass of this system and boom, boom, that all the lasers pointing at. Crean una pesadilla de ingeniería, ya no de física. La física está probada. The physics is tested. It works. Einstein's equation works. Okay? The problem is now how engineers manufacture this possibility. That's when the challenge is. So if you want me to bet my own money, I would not bet it on these companies. My way, humble approach.
¿Y el tokamak o en este ladito?
Buena pregunta. Quiere invertir, ¿no? yo soy formado en tokamaks. Y inclusive el récord que hemos logrado ahora en Francia es en un tokamak. Sin embargo, acepto que el tokamak tiene una limitación enorme, ¿no? El tokamak a usted le confina un plasma y el plasma carga corriente. La corriente que los tokamaks necesitan van a ser en el futuro entre 10 y 15 megaamperios. Megaamperios. Como dicen ustedes, es una pasada, ¿no? Me gusta más el Stellarator. El Stellarator es un modelo que implica que todos los campos magnéticos que confinan el plasma son producidos por imanes externos. ¿Se acuerdan que yo les contaba que en el tokamak este campo, el poloidal, está creado por la corriente, ¿no?
Sí, sí.
En el Stellarator está creado por los imanes alrededor. ¿Okay? Entonces, prácticamente uno turn on the machine y turn off the machine como si fuese un microondas de la casa.
Más circula igual.
El plasma circula, sí, ¿no? Porque hay una rotación intrínseca que depende de la energía del plasma, pero el plasma circula a baja velocidad y el plasma se flota y se queda tranquilo. There are challenges, hay desafíos. El particle transport, el transporte de partículas no es el mismo que tokamak y se está optimizando. Entonces, hay una serie de locos trabajando con modelos numéricos para ver cómo se puede optimizar el Stellarator, porque tiene periodicidad, ¿no?
Sí,
Si bien es asimétrico,
sí, sí.
tiene una periodicidad de n igual a 4 o n igual a 5. ¿no?
¿Ese número viene dado por la física o por la ingeniería?
Ese número viene dado por el transporte de cargas rápidas en el reactor, ¿no? Y se está optimizando ese número. Si es 3, 4 o 5, ya se verá. El problema está en que mientras más sea ese n, mientras más alto es, los imanes van a ser más complicados. Y eso traduce en capital y produce al final un retorno de inversión diferente al que uno tenía calculado.
Tengo una pregunta, Luis. En el caso de tokamak, la energía la vas a extraer usando los rayos X, ¿no?
No. La energía del tokamak la voy a extraer usando los neutrones.
A los neutrones.
Estos neutrones se van a termalizar en este baño de litio, que también va a producir más tritio, ¿eh? Pero o si es un baño de litio, o si es lead lithium, or is it maybe a molten salt, like in fission reactors, it remains to be determined. Pero la energía se saca con la interacción de este neutrón con esta sábana, que los neutrones van a través de mi compadre así, y calientan la sábana.
Ok.
Y ahí sacas, hay una especie de termalización, agua, vapor de agua, turbinas, y la forma convencional de producir electricidad.
Y la inyección de material es a través de ports.
Sí, hay varias ports, hay varias puertas, por ejemplo, en el reactor de Francia que le enseñaba, si no me equivoco, hay 18 puertas toroidales, ¿no? Y hay puertas donde hay válvulas de gas. Entonces, uno introduce gas para asegurar que no tenga deuterio. Pero acuérdese de que el tritio no es natural. Entonces, uno comienza con un poquito de tritio. De ahí tiene que generarlo. Y esa generación pasa a través de estos neutrones, a través de esa sábana, que produce calor, pero también produce tritio, y el tritio se mete de nuevo. Entonces hay a lot of valves to put gas, or to put impurities, or to put tritium or deuterium.
Y en el caso de los láser, ¿también van a extraer con los neutrones de energía?
En el caso del láser, los neutrones tendrán que salir fuera de esa cápsula redonda que te enseñé hace un momento, ¿no? No, esta de acá. O sea, los neutrones, el neutrón pasa tranquilamente por un pedazo de acero de esta dimensión. Ni cosquillas le hace al neutrón,
Sí.
¿no? Entonces pasa por ahí a la sábana que hay, ¿no? pero me parece mucho más complicado.
También salen bueno, hidrógenos neutros, átomos neutros, o es muy poquito.
No, muy poquito, muy poquito. Dale.
No solo.
Tritio, no hay tritio en el mundo. Hay 25 kilos y ITER se va a merendar 14 o 15. Además se retrasa 10 años, es decir, que el tritio decaiga, vamos a perder el tritio que tenemos ahora. Necesitamos para un reactor futuro, etcétera, etcétera, algunas decenas, o sea, 15, 20 kilos para arrancar un demo. ¿De dónde vamos a sacar el tritio?
Nuestra esperanza era obviamente ITER. ITER se va a demorar 10 años para hacer todavía una descarga de deuterio-deuterio. La descarga de deuterio-tritio será 10 años después. O sea, tiene usted 20 a esperar, ¿no? En 20 años yo ya estoy retirado, ¿no? Yo tengo 53, en 20 años yo creo que Princeton me retira. La respuesta pueden ser CANDU Reactors, los que hay en Canadá, o los que hay en varios lugares.
Están cerrando CANDUs.
Sí. La otra respuesta puede ser esta compañía que se ha formado en Massachusetts, que se llama CFS, Commonwealth Fusion Sciences. Pretende desarrollar un tokamak usando high temperature superconductors para los próximos 3 años. El proyecto que le he comentado a Julio, que estoy escribiendo ahora con el gobierno americano para desarrollar lo que le llaman un Fire Center, pretende instalar cosas, y ojalá que con ustedes, en Spark, en esa máquina en Boston. ¿Ok? Y su idea es comenzar con deuterio-deuterio en 1 año y pasar a deuterio-tritio en el 2.º año. Es mucho más agresivo. Entonces, esa es una solución.
Y usar un plasma deuterio que genera tritio también.
Claro, el de deuterio-deuterio tiene 50% de producción de tritio, ¿no? Y puede producir ahí, pero quieren pasar directamente a deuterio-tritio para usar el litio para generar tritio, ¿no? Después, hay otras opciones, inclusive en España. Usted se ha enterado de Smith Domes, ¿no? Es un maravilloso proyecto que se está construyendo en Córdoba, en Granada, perdón, con el cual espero también colaborar. Tenemos una propuesta, una patente de cómo ver flujos de litio dentro de cámaras sí, usando rayos X en transmisión y en backscattering, ¿no? Y he contactado al director de Smith Domes, Ángel Ibarra, para hacer esto, y me ha dicho que para fin de este año van a haber 2 líneas de litio ya construidas, ¿no? Fuera de que funcione Smith Domes, que nadie sabe cuándo va a suceder, ¿no? Pero de repente podría sacarse algo de tritio aquí en España. Sí. Pero sí, es un challenge muy, muy fuerte. No tenemos otra solución, porque la otra fusión que proponen en el mundo es, por ejemplo, D-helium-3, deuterio y helio 3. Helio 3 hay en la Luna, ¿no? Entonces, y créanlo o no, y riámonos todos, hay compañías que se dedican a de repente sacar un retorno de inversión considerando viajes a la Luna. Es alucinante, pues, ¿no? Y no tenemos otra solución que los Estados Unidos ahora están invirtiendo mucho en proyectos para justamente cerrar este gap, este vacío que hay en el círculo de la energía de fusión, porque todos hemos hecho plasma physics, todos hemos hecho fusión. Nunca un laboratorio ha hecho lo que se llama tritium breeding, el fenómeno que usted está describiendo, ¿no? Y ese fenómeno de tritium breeding no es simple. Separar litio 6 y litio 7 por métodos convencionales incluye hasta mercurio y es extremadamente complicado y peligroso.
Existen empresas en España que están trabajando.
¿Ah, sí?
Sí.
Ah, excelente. No sabía.
Bueno, es cierto que por kilovatio térmico de potencia de un demo necesitamos toneladas de litio 6.
Correcto.
Toneladas, 40, 50 toneladas de litio 6.
Sí.
Eso es una demanda de desarrollo tecnológico a una escala,
enorme.
digamos, fuera de lo...
Sí.
pero conocemos las tecnologías.
¿Y usted trabaja en ellas?
Sí, sí, trabajamos.
Ah, que no tenía idea. Conversemos, porque edúqueme, porque no sabía. No sabía que estaban en España, lo que había en España.
Incluso empresas que están aquí en un radio de 30 kilómetros, en proyectos nacionales de investigación, trabajamos en desarrollos técnicos. Con el handicap, que son tecnologías de doble uso, lo sabemos muy bien.
Sí.
Tenemos limitaciones. España, en Euratom, etc. Pero por supuesto que es un target. En ITER vamos a probar algunas decenas de kilos de litio 6.
Sí, pero el problema es que si usted revisa el calendario de ITER, si no me equivoco,
Sí.
habían 4 o 6 modelos de blankets para la parte final de ITER.
Fase de T de ITER, TBM, esto que llamamos TBM,
Claro.
de blanket modules, que tienen litio 6 con unas cantidades ya relativamente industriales. ¿De acuerdo? Esto es investigación que paga el gobierno de España, la Comisión Europea, desarrollos. Absolutamente necesario, visto la falta de combustible que tendremos. Estamos desarrollando Ferraris y no tenemos gasolina.
Sí, por supuesto. Esa es
Un poco
la analogía.
La gasolina, pues es el litio.
Sí, estoy totalmente de acuerdo. Yo le comentaba a Julio que ahora estoy metido en un proyecto que se llama el FIRE. FIRE es un acrónimo para Fusion Innovation Research Engine, ¿no? Y yo estoy aplicando a uno para tecnología. Son proyectos de $20 millones. Y hay alrededor de 200 millones en el portafolio, de los cuales yo creo que 100 van a ser dedicados solamente al blanket modules. Y usted va a tener la posibilidad de compartir experiencias con gente de, por ejemplo, Savannah River, ¿no? Donde tienen mucho litio. Tengo entendido que tienen una forma nueva de separar litio 6 y 7. Yo la desconozco. Pueden ser cosas más de orden de seguridad nacional, a lo cual yo no tengo acceso. Pero es algo muy importante para esta fusión. Como dice usted, tenemos Lamborghinis y Ferraris y no tenemos la gasolina adecuada.
Sí, es la auténtica situación.
Sí.
Creemos en la fusión, por supuesto, somos creyentes, ¿de acuerdo? Con mucha fe, ¿no? Pero en el camino hay desafíos que a día de hoy no tenemos.
Sí. Gracias por su comentario.
La última pregunta.
Sí. Sorry, I was mixing English and Spanish.
No, it's great for me to try to pretend that I understand. Well, my question is maybe naive, maybe I'm missing something. Like in your experiment now, you were saying that at some point, I suppose, like without taking this into account, you had this high temperature melting some cables, or what was it that you didn't take into consideration?
Yeah.
And your plasma, because of this, lasted for 6 minutes. So then you're planning to redo the experiment to cover these places with some material, no, that would sustain this technology. So you're now, let's say, taking this with precaution, but you say that your plasma will then roughly be around 10,000 seconds.
1,000 seconds.
But why do you? Because what is your limitation factor now? What's going to happen now? What's going to?
The 1,000 seconds are limited because this is a very old tokamak, the one in the south of France. Okay, they didn't prepare for something longer because they thought ITER is actually next door in CEA in France, in Cadarache. Okay, so they said, okay, why don't we put as a limit as 1,000 seconds because ITER is going to be available in 2025, correct? Okay, so they designed a cooling system according to the 15 or 18 megawatts of input power and 1,000-second shot, and the cooling system will take care of that heat that comes out, okay? Now, as he was saying, ITER is going to be delayed 10 years. So some French are pretty happy because they can operate west, next door, for another extra 10. So the question is, what would they do to maybe go from 1,000 seconds to 10,000 seconds? They might need to change their cooling system. It might not be that expensive, by the way. Okay, so they are already thinking on that possibility.
there are no more questions, I think we can.
Gracias, muchas gracias.
Thank you very much. Very interesting talk and also interesting discussion.